So last time we learned a few ideas about how to compute some limits for pretty simple functions. And today what we're going to learn is how to compute limits for much more complicated, much more interesting things. And our big theorem today is going to be theorem 2.7, functions that agree. This is going to help us figure out how to compute just a whole bunch of different limits that we couldn't before, and pretty much everything is, we're going to be able to compute everything now. We're going to be that strong at limits. So yesterday we looked at a certain limit, said that suppose we want to find this limit here. The limit is x approaches 2 of x squared minus 4 over x minus 2. And this looks like a nice rational function. Maybe we should try direct substitution. So direct substitution says, well, let's just substitute in 2, so we get 2 squared minus 4 over 2 minus 2. This is, let's see, 4 minus 4 over 2 minus 2, showing all my work. Well, this is 0 over 0. So, well, what do we do with that? We can't divide by 0. That's bad. So this is definitely not going to work. Direct substitution fails. Well, maybe this thing just doesn't have a limit. So let's look at the graph. So if I look at the graph here and I think to myself, well, what happens with values as we get closer to 2? Well, the problem is it looks like we are going to get closer and closer to 4. So this tempts me to think that the limit maybe, as x approaches 2 of x squared minus 4 over x minus 2 really does have a limit, and its value is going to be 4. But what we want to do is we want to develop ways so we don't always have to go to the graph, we don't always have to go to a table in order to figure out these limits. We can do them much more efficiently, and this is going to help us later when we want to do them much more abstractly. And so the key here to think about is that if we look at this graph, well, it looks pretty much like a line. And in fact, it looks like the graph of the line y equals x plus 2. The key difference is that we have a solid dot here at 2, 4 on the graph of our line, whereas over here we have a hole in our graph. And this comes from the fact that in the denominator of the function on the left, we have x minus 2, which means we can't just directly substitute 2 in. It doesn't work, whereas on the graph on the right, the line, we can substitute 2 in. And just for kicks, let's look here. Let's see, the limit as x approaches 2 of x plus 2 is going to equal 2. And so what we want to do here in this section is our goal is to go through the following theorem that says that basically limits can't tell the difference between these two functions, that these little holes in the graph limits don't care about them, they can't see the difference, and to limits these two functions are the same. So when you're computing a limit, sometimes what you can do is you can replace a function that looks kind of bad with a function that's really easy, a nice polynomial function or a nice simple function we know how to compute the limit of pretty easy and efficiently. And so what we did in the previous page is basically what this theorem tells us. Theorem 2.7 says functions that agree at all but one point, and we're often going to abbreviate this as FTA. And it says that if you have yourself a real number and you have two functions that basically look the same, they agree except at one point, then if the limit as g of x as x approaches c exists, then the limit of f of x exists and the limits are equal. Basically, you can replace a bad function, f, with a good function that you can compute the limit of. So let's see how this works. So if we remember from the function we were just looking at, x squared minus 4 over x minus 2, well, what we can do is we can factor the numerator here into x minus 2 times x plus 2. The denominator is still x minus 2. And then probably in algebra you're always told, well, let's just go ahead and cancel these things. And so we're left with x plus 2 as long as we remember that x cannot equal 2. That is, these two functions are the same as long as we remember this extra thing that we better not use x equals 2 in there. And so what this theorem tells us is that when we use limits now, we want to take the limit as x approaches 2 of x squared minus 4 over x minus 2. Well, what we can do is we can rewrite this here. We can factor. And now here's the key step right here. This equality is the equal sign coming from the theorem. It says that this limit is going to be the same as this limit in canceled form. And now that we're left with just a simple polynomial, we can go ahead and directly substitute in to get 2 plus 2 equals 4. What this theorem tells us is we can replace this difficult function here, f, with a simpler function here, g, in order to compute the limit, because these two functions here are exactly the same except at a single point. These two functions are equal except when x equals 2. This first function had a hole in it, whereas this function is nice and continuous and it doesn't have any holes in it. Therefore we can just factor and cancel, and the limit doesn't care. The big thing to think about here is that sort of limits have bad eyesight. They don't see what happens at a point, but they see what happens around it. So that's almost a better way to think about the theorem, is that it doesn't really matter what happens at a single point, just in the neighborhood around it. So let's look at another example of this. So let's try to compute the limit as x approaches 3 of x minus 3 all over x squared minus 9. Again, it doesn't hurt. We could always just try to do a direct sub and see what happens. So we just put 3 in there, and unfortunately we end up with 0 over 0. And so what we've said before is this is going to be called our indeterminate form. And so an expression such as 0, 0 is called indeterminate form. We can't determine the limit yet from this alone. The limit could exist, it might not exist, we need to try something else. So in this case we're going to try to use the theorem that says let's try to replace this function with a function that agrees with it except at one point. So what we're going to do is we're going to try and factor this function. And so what we can do is we can factor the denominator there. The numerator is already pretty nice looking, into x minus 3 times x plus 3. We can see that the x minus 3's will cancel, and so by the functions that agree theorem, so this theorem 2.7 we just talked about, we can now instead calculate this easier limit of 1 over x plus 3 as x approaches 3. And since this is a nice rational function, we can now calculate the limit exactly by direct substitution, and I just wrote it again there for fun as 1 over 3 plus 3, so our limit ends up being just 1/6. That is, we can calculate this limit pretty easily by just factoring and canceling because we had this 0 over 0 form. So let's do a few more examples just to make sure we've got this all figured out. So the limit as x approaches 2 of x squared minus 4 over x plus 2. Now, once you get good at this, you might be tempted to say, well, let's just factor and cancel and see what happens, okay? The thing is, though, is that in this case, you don't actually have to factor and cancel. This is a good rational function, and if we just go ahead and directly substitute in, we'll get 2 squared minus 4 over 2 plus 2 this time. So 0 over 4. Well, 0 over 4 we can divide by 4, and so the limit's just 0, just by directly substituting. We didn't have to mess around with any factoring or canceling here. This was sort of it's a good trick question. Another thing that might happen when we have to compute a similar looking limit is we might have x squared plus 4 over x minus 2. In this case, we get the indeterminate form, or not really an indeterminate form, but nothing really. If we try to directly substitute, we'll get 2 squared plus 4 over 2 minus 2. Well, that's 6 over 0. Well, that's not good. We're not going to be able to factor and cancel in this case because we got a 6 up here instead of a 0. In order to factor and cancel, we need to remember the factor theorem of algebra, which said that if you have yourself a 0 of a polynomial, then x minus c is a factor. That is, if you have a polynomial, you put a number and you get 0, then you can factor it. In this case, since we didn't get 0 in the numerator up here, we're not going to be able to factor x squared plus 4 to get anything to cancel. We're just out of luck. This limit does not exist, and we'd have to look at the graph or a table. Let's look at just one more example. The limit as x approaches 3 of x squared minus 4 over x minus 3. Again, if we try to directly substitute, what's going to happen is we're going to end up with now 9 minus 4 over 3 minus 3 is 5 over 0. even though this numerator are factors, we could write it as x minus 2 times x plus 2 over x minus 3. It doesn't factor in a way that cancels, so we're still out of luck. There's a lot of things that you have to look out for here. You really need 0 over 0 form in order to make any headway. So here are some general tips when it comes to computing limits. Step 1 is learn to recognize which limits can be evaluated by direct substitution. So remember that polynomials are your friends, rational functions, trig functions, constants, x to a power. These are all great things that we can just go ahead and substitute in and be on our way as long as we don't get a divide by 0 problem. If you do get a 0 over 0 problem though, that indeterminate form, you're going to need to find a function that agrees with it except at one point. Often this will be factoring and canceling. Often that's going to work. There's another technique we'll learn in a little bit here called rationalizing, which takes a little bit more work, but it's another way to get something to sort of cancel out. Third, apply theorem 2.7, that is the theorem we've been calling the functions that agree theorem, to conclude that the limits agree and is g of c. This way you can directly substitute and solve. And last, graph or use a table to reinforce your conclusion. Now, graphing or just using a table alone is not good enough. That doesn't constitute a good way to answer the problem. We really want to use these one of a very algebraic way to get the right answer, because graphs and tables can lie to us. But it is an excellent way to get a good start on what you should expect to happen. It's a good way to check your answers. It doesn't hurt to check. Often graphing is a good way to make sure you're on the right track. So sometimes we can't actually factor, but we do get an indeterminate form, in which case another technique that's useful is called rationalizing. So in this case we have this limit presented here, the limit as x approaches 4 of the square root of x plus 5 minus 3 all over x minus 4, and what we could see is if we had tried to do a direct sub, what we're going to get is we're going to get the square root of 4 plus 5 minus 3 all over 4 minus 4. We can see our denominator is headed in the indeterminate direction, and our numerator gives the square root of 9 minus 3, which is again 3 minus 3. So 0 over 0, we've got ourselves an indeterminate form. So this was a good thing to check, but we cross it out because it's useful or useless. And now what we need to do is we need to try something else. And if we stare at this thing, well, I can't factor that. So I need to try something different. Instead, what I need to do here is I need to rationalize. So rationalizing, you may remember way back, as something you learned in algebra in order to clear out denominators, because for some reason people decided a long time ago that 1 over the square root of 2 was ugly, but the square root of 2 over 2 was nice to look at. We don't want radicals in the denominator. I don't know why this is true, but it's something you learned a long time ago. Anyways, it's a good technique to use here. So the key to rationalizing is to recognize that that square root thing is bad, and so we want to get rid of it. So what we need to do is we need to multiply by something to get rid of that bad part. So what we're going to do is we're going to multiply the top by the bad part, the square root of x plus 5, but in this case we're going to do plus 3. And whenever we multiply a numerator, we've got to multiply the denominator by the same thing so that the blue part cancels and just gives 1. Now why did I choose this crazy thing? Why did I choose a plus there? Well, let's see what happens now when we multiply this out. So when I distribute, I'm going to get the square root of x plus 5 times the square root of x plus 5. I'm also going to get plus then 3 times the square root of x plus 5. And now I'll get minus 3 times the square root of x plus 5. And finally, minus 3 times 3 all over, never ever multiply out the other part. It's just going to give you a lot of headaches if you do. So just leave those there. And now we can see what happens after we simplify this down a bit. Well, this first part's nice. the square root of x plus 5 times the square root of x plus 5 just becomes x plus 5. That is, we add the half exponents, we get 1/2 plus 1/2. What's neat is now we have a plus 3 times the square root of x minus 5 minus the square root of x plus 5 times 3, so those cancel. That's why I changed from plus to minus. And last, we end up with minus 9 all over, we keep our denominator the same. And you're probably saying to yourself, Professor Williams, with all due respect, we've just made a mess here. And I agree, it does look messy, okay? Not only my handwriting, but also what we've written. So let's clean this up and see really why have I done this? What have I done by replacing this function with this one instead? So my goal was to compute a limit over here. It was an indeterminate 0 over 0 form, and now I've done a bunch of algebra and I've ended up with this mess over here. Well, let's keep going and see what happens now. So now I still want to compute the limit. I haven't done that part yet, but I can simplify my numerator a little bit down here. So what am I going to get? Well, x plus 5 minus 9 becomes x minus 4, and in the denominator I've got myself an x minus 4 times the square root of x plus 5 plus 3, and guess what? Those x minus 4's cancel. So now I'm left with the limit as x approaches 4 of 1 over the square root of x plus 5 plus 3, and I think I'm in good shape here. If I just directly substitute, I'm no longer going to get that pesky divide by 0 problem, because I'm not dividing by x minus 4, so I'm no longer going to divide by 0. Instead, I'm just going to divide by 3 plus 3, so I end up with a limit of 1/6. So I was able to replace my function with something simpler by doing this rationalizing technique. So here's one that I'd like you to try on your own. The limit as x approaches 0 of the square root of x plus 5 minus the square root of 5 all over x. And you should fill in all these steps correctly, and hopefully if you do everything right, you'll end up with a limit of 1. Try it on your own and see what happens. So the last thing we're going to talk about today are 3 special limits that we'll often see involving trig functions, as well as the number e at the end there. And we want to talk about how are we going to make use of these. And often they're going to be very useful when you face difficult looking trig problems. For example, if we even just look at this, well, let's look at the first one first. So if we look at the first one, this says the limit as x approaches 0 of sine of x over x equals 1. So if you directly substitute, it's definitely an indeterminate form, and you do have to go through a bit of work to see that it actually is 1. But rather than going through that, let's see how to make use of it in looking at problem number 2 here. So in problem number 2, we take the limit as x approaches 0 of 1 minus cosine of x all over x. And we could try to directly substitute. The problem is we get 1 minus cosine of 0 all over 0, so this is 0 over 0 form, and we're in tough shape. This is an indeterminate form, so that's not going to work. Instead, what we want to do is we want to rewrite this using the idea we came up with of rationalizing. So here we have a 1 minus cosine of x over x, and we can actually use the rationalization idea. So the rationalization idea says, well, what we're going to do is we're going to multiply, instead of 1 minus cosine x, 1 plus cosine x all over 1 plus cosine of x. The reason we want to do this is because trig functions are pretty nice. When we multiply this out, we end up with 1 minus cosine squared x all over x. Don't multiply the other part out. And of course, we remember all our trig identities. 1 minus cosine squared x is just going to be sine squared x all over x times 1 plus cosine of x. And here's the real part where you have to get pretty good at limits to see it, but what we can do is now we can break up our limit into 2 separate fractions here. So that sine of x squared, we can break those signs up into separate fractions. So we're left with separate limits here. And the reason we want to do this is because these are two limits that we can compute. The first limit there, sine of x over x, is exactly number 1 up in the table up there. So this limit just becomes 1. And the other limit over here, well, as x approaches 0, what we're going to get is we're going to get 0 in our numerator and 2 in our denominator, so 0 over 2. So overall our limit becomes 0, just as we'd hoped. The key was to rewrite trig until we ended up with this limit that we know how to compute. And so you'll have a few examples of these where you're going to need to rewrite until you end up with a limit that you can actually compute. Now these are definitely going to be the tricky ones because you have to remember your trig identities, but we will definitely talk more about these in class. So there's some problems listed on the website on Blackboard for you to try. You should also list a question and then come to class and we'll talk more about these tomorrow. Thanks.